Good morning, my name is Anna POGREBNA, I'm from Radboud University, and for next half an hour I want to talk about ultrafast and equilibrium magnetism anomalies, which are observed in rare earth transition metals in high magnetic fields. And by high magnetic fields I do mean high, up to 37 Tesla. But before moving to our project, I would like to acknowledge all the people who participated in. First of all, it's people from our group at Radboud University. Experiments were done with help of Kiran Prabhakara and Jonas Becker. And also we got great support from Alexei Kimel and Theo Razing. The high magnetic fields were provided by High Field Magnetic Lab in Nijmegen. I will talk about this unique facility a little bit later. The samples were provided by Professor Tsukamoto from Japan, and we got really great theoretical support from a group of Professor Zvezdin from Moscow, and all the calculations were done by very talented master student of Professor Zvezdin, Margarita Davidova. So let me move on. We all gather here because there is society need for ever faster and ever more energy efficient data storage and information processing, right? And there were already multiple very successful realizations of magnetic control by electric current, electric field, and light. And however, not all the mechanisms are clearly understood so far. And it is really well established that exchange interaction and spin orbit interaction play a decisive role in control of magnetization. And thus the objective of our study was to apply magnetic fields which would be high enough to compete with those interactions, and then study new unrevealed before magnetic phases by means of ultrafast laser pulses. As an object for this study, we have chosen rare earth transition metal alloys, which were already introduced in previous works. But I want to remind you that it's a ferrimagnet, so it has two magnetic sublattices which are not compensated and antiferromagnetically aligned. And often in these materials, the temperature dependence of magnetizations is different. And this fact enables the situation where two magnetizations compensate each other and net magnetization is equal to zero, and this is so-called compensation point. Moreover, it is known that if you put this kind of material into high magnetic fields, you can really reach a whole spectrum of magnetic phases, from antiferromagnetic to candid ferromagnet and to ferromagnet. But of course, for that, you need really high magnetic fields. In the world, there are few facilities where you can really apply high magnetic fields. But there is only one unique facility where you can combine high magnetic fields and ultrafast laser pulses. And it's situated in Nijmegen. So our optical lab looks like following. We have 1 kilohertz laser system. It's titanium sapphire with OPA, so we can tune the wavelengths, 50 femtosecond laser pulses. And on top of that, in this case, it's in bottom of that. On the first floor, we have a huge magnet. It's an electromagnet, and we can apply DC magnetic fields up to 37 Tesla in this setup. Closer, my experiment looks like following. We are measuring in a normal incidence geometry. The anisotropy field is aligned out of the plane, and then magnetic field is also out of the plane. First measurements done on this facility were by our group. On gadolinium, iron, cobalt. This is the result. This is pump-induced smoke effect as a function of delay. And as you can see, the dynamics is strongly influenced by the magnetic field. At small magnetic fields, the dynamics is pretty fast. It's on few picosecond time scale. However, when we increase the magnetic field, it's getting way slower and the amplitude increases, and then it gets again faster at very high fields. So this is how it looks like when we plot the rise time as a function of magnetic field. You see that there are obviously two different regimes, very fast dynamics below 4 Tesla and very slow dynamics above that. And the hypothesis of this paper was that somewhere here around 3 Tesla, the spin flop transition occurs. What does it mean? That below that transition, our magnetizations are aligned antiferromagnetically, and then the dynamics observed by our pump probe is associated with the demagnetization. That's why it's so fast. However, above the spin flop transition, the magnetization become tilted with respect to each other and to magnetic field applied, and then the observed signal is associated with the tilt of magnetization. That's why it's getting slower and amplitude is increasing. To check this hypothesis, also the static MOC measurements were done, and indeed, above the coercive field, you see at all temperatures you observed one more transition, which had a second order in nature, and indeed we associated with a spin flop transition depicted here. So you see at spin flop field it gets counted and there is some angle, and then at very high fields we come to ferromagnetic phase, but we never actually reach that high fields in these experiments. To get a better understanding what's going on here, the usual way is to plot the phase diagram where we plot characteristic fields as a function of temperature, and you see that around the compensation temperature, there are all interesting things are happening. So there is coercive field, which tries to diverge at the compensation temperature. It's natural because we are approaching the antiferromagnetic state, but then it does not because of emergency of spin flop transition. So it stops around 3-4 Tesla. And the second question we are asking ourselves, what would happen if we change gadolinium, substitutes gadolinium iron with terbium. As far as terbium has non-zero orbital momentum, that's increase in spin-orbit interaction in this material. So would it change the phase diagram, and what are new phases we can observe and study there? So this is our study, our results on measured on terbium iron cobalt. These data were taken at low temperature, far below the compensation temperature, and the wavelength of probe was 1.5 eV, so very sensitive to iron cobalt sublattice. You see that dynamics again strongly depends on magnetic field. At small fields, it's very slow, and then it's getting faster when we increase the magnetic field. And this is how the relaxation time looks like a function of magnetic field. So you see there is like divergence slowing down around 5 Tesla. If you look closer at the rise time, we observe quite similar behavior. The rise is on tens of picoseconds, but then again it's diverging when we approach 5 Tesla. Okay, what happens when we go to really high temperatures, far above the compensation? You see that dynamics changes quite drastically. We start observing two different regimes. At small fields, there is very fast dynamics on picosecond time scale, and it's changing sign. But then when we apply higher fields, it's getting way slower, and again fastens when the field gets stronger. So this is how it looks like. You see that there are two regimes, quite similar what was observed in gadolinium, and something is happening between here, 10 and 15 Tesla. And when we look at the rise time, the behavior is similar, with only difference that in this case there is no divergent slowing down around 12 Tesla. It's only slowly goes slower. Sorry. So to understand what happens in this case around 12 Tesla or 5 Tesla below the compensation, we performed static MOC measurements. I'm going to show you static MOC as a function of temperature. The compensation is at 321. sorry, here was a typo. It was 321. Yes, and I'm going to use the fact that in terbium, iron, cobalt, depending on the wavelengths of probe, you can probe separately iron, cobalt, or terbium sublattice. So first I will show you static results for iron, cobalt. So this is how it looks like. Looks very complex at the first look. If you start with a simple case, low temperature, far below the compensation, so hysteresis looks quite simple, it's just one loop. But when we heat it up and approach closer to the compensation, there appears some kind of kink, which could be a second order phase transition. But when we cross the compensation temperature, this kink becomes a sharp jump. And at high temperatures, we clearly see that there are 3 different hysteresis loops separate, which is quite unusual. And then we checked, we did same measurements for terbium sublattice, and you see that it's exactly same curves. However, the sign is different. And again, to make a summary of all this data and understand what phase transitions or phases we observe, we also plot H-T phase diagrams. So we will show all these abrupt changes with black points and smooth changes with blue dots. So this is how it looks like. This is our phase diagram, experimental one. You see it looks quite complex, and there are clearly many transitions and many phases. To explain it, we first look through the literature if there are any explanations for rare earth transition metals, which would explain this kind of figure. And so first we have found that actually those funny 3 hysteresis loops are not new, and they were observed before in Hall effect transport measurements in rare earth transition metals. And main approach used to explain them was a so-called two-layer model. So this model implies that magnetization of rare earths and transition metal are not homogeneously distributed in the material. And then there are formed some kind of layers where minority and majority spins are distributed. And then the hysteresis loops are formed in this way. So there is one big loop in the middle, which comes from majority layer, and then there are 2 smaller loops which come from minority layer. Okay. So, but problem with this model is there are a few problems. First of all, it implies that we don't have that good quality samples. And second of all, it doesn't really explain this huge exchange for minority layer. So we decided that it's not really satisfactory to explain it like that. And then we developed a theory which is based on paramagnetic rare earth ion approximation, in which we write the thermodynamic potential in this form. H effective here is an effective magnetic field which acts on rare earth ion from transition metal sublattice. The last term describes an actual anisotropy field, which is given as following. And here Kd and Kf are magnetic anisotropy constants. I will not go into details of these. But I want to say that the main assumption of our model was that anisotropy comes only from a rare earth sublattice, and it's almost 0 for the transition metal sublattice. Okay, and this is our result. As you can see, it perfectly actually describes the experimental observations. Below the compensation, we observe 1 hysteresis with some kink, while above the compensation, we do observe a 3-loop hysteresis. Okay, and then by minimizing this potential, we could obtain the phase diagram. This is calculation. And here, blue line corresponds to the second order phase transition where spin flop occurs. Black lines correspond to the stability loss of each phase. And we observed 3 different phases. 2 of them are antiferromagnetic phases. with a different orientation of spins. And a third phase is a contact phase, which occurs at higher fields. Also, our theory predicts very interesting feature. Somewhere here at higher temperatures and higher fields, there is a three critical point where this transition from collinear phase to non-collinear phase turns from first order to second order, but that would be a subject of a separate high magnetic field study. Okay, so this is what we get for statics. You see that this is experimental data and this is our modeling, and it's quite perfect. Now when we understand this without implying any inhomogeneities or huge exchange bias fields, we are of course interested if we can explain the dynamics by means of this. And yes, we do. Our hypothesis was right, and indeed this all slow dynamics we observe in the contact phase. And it is associated with the tilt of magnetic moment, while this very fast regime is for the antiferromagnetic phase, and the signal is associated with the demagnetization. But then what's the deal with this divergency around the transition, and which is absent right here? Can we explain that by theory? And yes, indeed we can. So we wrote down the Landau-Lifshitz-Gilbert equation and modeled the changes of magnetization as the time delay for different magnetic fields. And I want to put your attention to this main result. As you can see, around second order phase transitions, both rise time and relaxation time show divergency. Okay, while it's not predicted for first order phase transitions, that's why we didn't observe it for here. Okay, and before going to conclusions, I would like to show you one more interesting feature of our measurements. As I already mentioned, terbium and iron cobalt sublattices can be measured separately, and we also did all the same measurements for terbium sublattice. And you will probably already get your attention to this graph, where dynamics is quite different for two sublattices. There was already a spoiler that F ions can be slower than D ions, but as you can see, it's twice slower in this case. So let me conclude on that. We have developed a theory which describes really well equilibrium magnetism in rare earth transition metal alloys. We have described anomalous hysteresis loops as a series of first-order phase transitions, and this model also helped us to describe the dynamic properties. Thank you very much.